Hi everyone, and welcome to our lecture video all about collecting gases over water. By the end of today's lecture video, you will be able to calculate the partial pressure of a gas collected over water using your previous knowledge of Dalton's law from last class, and also be able to calculate the amount, the pressure, or the moles of a gas produced in a reaction. Today's lecture video is being taught to you now so it can set you up for our next class where we are going to be doing an experiment to collect gases over water. And after this lecture video, you will be able to calculate and do the quantitative questions for your pre-lab homework. So, to understand a little bit about what this laboratory experimental setup looks like, let's go ahead and start with a video. So in this video, we're going to be watching what's happening, and we're going to be doing a very similar experiment in our next class. This scientist here is going to be dropping a piece of magnesium into this hydrochloric acid right here. And what's going to happen is the hydrochloric acid mixing with the magnesium produces hydrogen gas. And as this gas is produced, it's going to come up and around, and it's going to come down in this tube through the water, and we're going to start to see some bubbling occur, but I'll let the scientists take it away before talking a little bit more in depth.
Collecting gas over water is an efficient way of obtaining small samples of gases in the laboratory. It works well for any gas which does not dissolve in water easily. For this demonstration, I am going to react hydrochloric acid with magnesium, which of course produces hydrogen gas. The beaker acts as a water reservoir in which there are two upturned water-filled test tubes. If one of these tubes is placed over the end of the delivery tube, every bubble of gas can be seen as it is produced.
Okay, so what we started to notice, and we're going to see this in another diagram in just a moment, as the hydrogen gas is produced, it can be collected. In this case, it was collected into test tubes, and each of those test tubes were filled with water. But as the hydrogen gas was starting to collect, the gas displaced some of the water, which pushed it out of that test tube. Ultimately, what looks like empty space over here was actually hydrogen gas being collected. So let's see another diagram here. Here we have the reaction KClO3, and when KClO3 is burned in the process of being exposed to a Bunsen burner, it produces potassium chloride, KCl, and oxygen gas. So what's happening here is that as we're burning this KClO3, the remainder solid stays right here, but since we produce a gas, the gas is going to start to move. The gas is going to move through this test tube here into the glass tubing, and it's going to continue on its way down through here and then go up into what looks like an upside down mason jar filled with water. As the oxygen gas is produced, it bubbles through. That's why we see the bubbles right here. And it starts to displace our water. So what looks like this empty space up here is actually just pure oxygen gas being produced. So what looks like an empty volume, so to speak, this is actually filled up with the oxygen gas that was produced in this reaction. However, we have to take into account that we are collecting this gas over water. So what happens is as this oxygen gas is produced, it occupies this empty volume, but because we have gas over water here, we also are going to have water vapor present. So in this empty quote unquote empty volume up here, not only do we have oxygen gas, but we're also going to have water vapor, or H2O gas. And the amount of water vapor that we have is going to be dependent on the temperature of its surroundings. Typically, we're still going to have a lot more oxygen than we are water vapor, but we still have to account that inside this volume right here, not only do we have oxygen gas, we also have water vapor or gaseous water as well. So if we want to ultimately figure out maybe how much water is produced, we have to account, utilizing our understanding of Dalton's law of partial pressures, that the pressure inside this volume right here isn't just from my oxygen gas, it's also from my water vapor. So the gaseous mixtures is a result of gas collection over water due to the displacement of water. Ultimately, in this volume, we have a mixture of gases. Our mixture of gases, we have water vapor, and we have the gas that's produced from the reaction that we're doing. In this case, inside this empty volume right here, we have oxygen from this reaction down here, and we also have water vapor. So it's important for us to be able to identify that when we collect gases over water, water vapor, aka gaseous water, is produced, which contributes to our overall pressure. So this is a really helpful laboratory technique because it allows us to completely collect all of the gaseous product that's produced in a reaction. But we also have to make sure that we account for the water vapor before determining properties of just my oxygen gas. So I'm going to talk us through a practice problem. These practice problems are very similar to what you're going to be seeing on your pre-lab questions. And like we talked about in our last class, I'm going to talk us through how we identify what we're given in a problem and how we ultimately work our way through to be able to answer the questions we're being asked. So we're given what looks like a lengthy problem. I'll read it first, and then we'll go ahead and dissect what we're given. A sample of solid potassium chlorate, KClO3, was heated in a test tube and decomposed by the following reaction. That's exactly what we just saw right over here. So 2-KClO3 decomposes to form KCl and oxygen gas. The oxygen produced was collected by displacement of water. That's our first key, displacement of water at 22 degrees Celsius at a total pressure of 754 torr. The volume of gas collected was 0.650 liters, and the vapor pressure of water at 22 degrees Celsius is 21 torr. It's asking us, calculate the partial pressure of oxygen gas, O2, and the mass of oxygen that was produced. So in a lengthy word problem like this, let's break it down and understand what we are given. Starting with the first piece of information, we're told that our experiment is happening at a temperature of 22 degrees Celsius. We're then told that our total pressure is 754 torr. When we're given a total pressure, that's going to be the pressure of our atmosphere, of our environment. So our total pressure, we're able to say that it's the pressure of our atmosphere, and we set that equal to the 754 torr that we were given. Next, we're told that the volume of gas collected is 0.650 liters, and the vapor pressure of water is at 22 degrees Celsius is 21 torr, which means at our laboratory experiment temperature, that's the pressure of water vapor that would be produced in our empty container. So to calculate our partial pressure of O2, if you see the key term partial pressure, that's a good indicator that we're going to want to go ahead and utilize Dalton's law of partial pressures. So to calculate our partial pressure, because we're doing a displacement over water, we're able to say that the pressure of our atmosphere has to be equal to the pressure of our water vapor in this case, plus the pressure of our oxygen gas. Conveniently, because of our experimental conditions, we know the pressure of our atmosphere is 754 torr, so we're going to be able to plug that in. And we're also told that at 22 degrees Celsius, our vapor pressure of water, which means our pressure of water vapor, is 21 torr. So we're going to be able to plug that in here. When I plug those in now, I can ultimately solve for my partial pressure of oxygen gas. And when I subtract that, I get my partial pressure of oxygen gas to equal 733 torr. That means in that empty space that was collected, we had 21 torr of water vapor, and we have 733 torr of oxygen gas produced in this reaction. So that's our first question. We calculated the partial pressure of oxygen gas. Next, we're able to say that we have to calculate the mass of oxygen gas that was produced. So let's take this and add it to our given information over here, because this is going to be helpful for us moving forward. If we're asked to calculate the mass of oxygen gas produced, that should indicate to us that I'm going to need to figure out how many moles of oxygen gas are produced. And the way I figure out how many moles of oxygen gas are produced is utilizing our favorite ideal gas law, or PV equals nRT. So to get our mass, we need to know how many moles of oxygen gas are produced. So we're going to use PVnert to get us on our way. But because we're using PV equals nRT, I have to make sure that I plug in the correct units. So I'm given my temperature in degrees Celsius. I have to convert that to Kelvin in order to plug it in and for it to be useful in our ideal gas law equation. Not only do I have to convert this to Kelvin, I also have to convert my torr to atmospheres, because I have to plug in atmospheres into my ideal gas law. So I divide by 760 torr to say that 733 torr is equal to 0.964 atmospheres. My liters are ready to go, so we can now go ahead and start to plug in. PV equals nRT. I'm isolating my number of moles because that's what I want to solve for, and say that my number of moles, N, is equal to PV divided by RT. I plug in what I'm given. My N is equal to my 0.964 ATM times my 0.650 liters, because that's the volume of the gas that we're given, divided by my ideal gas constant, 0.08206 liter atmospheres per mole Kelvin, times my temperature. When I plug this into my calculator, we find out that this produced 0.0259 moles of oxygen gas. But I don't need to know my moles. I'm asked about my mass. So to get my mass, I have to utilize my molar mass and say that for every 1 mole of oxygen gas, because it's O2, we ultimately have 32 grams of O2. So when I multiply 32 into 0.0259, we're able to say that 0.83 grams of oxygen gas are produced. So now we've talked through a more complex collecting over water example, and now you should be able to utilize this knowledge to answer your pre-lab questions before we do this actual experiment next time in class. I'll see you then. Bye, everyone.